So now we will discuss some more advanced things in this topic. And this is parametric effects, oscillations in multilayer medium, and neutrino-neutrino scattering effects. So what are these parametric effects? Actually, it was paper, first one, in '86 by Yermilov, Tsarev, and Chechen, which was published in some journal which belongs to Lebedev Institute. Nobody actually practically know about this paper. And this was about the time when MSW papers have been published. And what they mentioned is the following, that actually strong transitions can occur if the density profile has harmonic modulations. So their goal was to see if there are some other possibilities of strong transformations of one neutrino species into another one without, say, resonance effect or without large mixing. So what they are saying, so suppose your density profile as a function of x has the following form. It's some average multiplied by periodic function of x, where omega is frequency of these modulations. So if the frequency of these modulations equal, so multiplied by integer, equal to eigenfrequency of your system, also to say difference of eigenvalues of your system, which is given by this expression, you saw this already before, then you have parametric resonance, which is nothing but, again, coming to pendulum analogy. If you have pendulum, and if you knock this in certain moments of time with a frequency which coincides with the frequency of your pendulum, then you will have enhancement of oscillations. So if this condition is satisfied, so that density frequency of density modulation times k equals to this one, then instead of this type of the oscillation effects, you would have this one. And this is the probability of transition as a function of x. So that these modulations lead to enhancement of the transition. And if you are sitting at resonance, at some point, at some distance, you will have maximal transition of one neutrino species to another one. So independently, a couple of years later, Akhmedov considered this type of the profile, not periodic, not sine and cosine, but this so-called Castle-Wall profile, where you can get very easily a solution analytically and simple way. Actually, he didn't know about the paper by Yermilov, and I was a referee of this paper. And I said, look, it was some paper before, and look at this parametric resonance already has been found. So, but let us consider this example, and let me show you how enhancement of oscillations occurs, how this kind of growth of oscillation occurs, and I will use my graphic representation, which is shown here. So suppose I have this density change, so layers, alternative layers with different densities, and suppose I start with electron neutrino. Again, this is flavor space. And so I start in this position, electron neutrino. And in the first layer, suppose I have my B vector here. This is cone vector is here. So this is the first position. So my system starts to precess around this position of B vector. And suppose, and here parametric condition enters. When I enter the second layer, here, the phase of this precession is pi. So that when I enter point 2, the second layer, I'm here. At this point, density changes, and therefore in the second layer, my position of the vector, B, will be here. So this is B2, which is determined by mixing angle in matter in the second layer, is in this position. Then my polarization neutrino vector will precess around new direction of the B, and so it will make such a type of the motion, right? And point 3 corresponds when I am back to low density layer. So at the point 3, vector B jump back to position B1 because this is low density. And so that in the third layer, the system starts to precess around this direction. So it will make this motion. And so if I have these alternative layers, my vector B will jump from this to this direction, and my neutrino vector will do this kind of spiral motion. At some point, it will be converted completely from electron neutrino to tau neutrino. Okay? Well, approximately the same is for this periodic sine or cosine dependence, but physics is the same. So you have layers with different densities. Position of your vector B, axis of the cone, changes. And if it changes, correlating with the phase of oscillation, so that every time you have pi over 2 pi or 3 pi, when you enter from one layer to another one, then you will have this type of the motion. And then system will return back. So it will do this kind of parametric oscillations with maximal depth.
How can you tune the phase pi1 and pi2 to be
Yeah, I'm saying if, right? So if this is tuned, and then you will get this. But you see, the point is that the phase depends on energy, which means that at certain energy, for instance, this condition can be satisfied. And I will come to some realistic examples, actually. Very interesting.
Is there any possibility if we have more Kessler wall, then go back to the original?
Yeah. So this is what I'm saying. So that's 8 is somewhere here, right? And if it continues, then it will go back. And it will be continuously. So you will have something like this. You will have the form of P dependency. Okay? Now, what's interesting that the Earth profile looks like, part of this Castle wall profile. And so what we have is the mantle and the core of the Earth. So roughly speaking, this is the first layer of the mantle, then core, which has density, say, factor of 2 bigger, and then again mantle. So that neutrinos which cross the core of the Earth will kind of see this type of the profile. And then you will have enhancement of oscillations due to this type of parametric resonance here. So this is a realistic situation which is satisfied at some values of parameters, and that must be observed, actually. These are some energies, some 4.3 GeVs, and this is the angle. So it's not a joke, right? So that is a realistic computation of probability, so that instead of this type of the change of the, so instead of this type of the oscillations, you would have continuous increase, and you will get 1 here due to this specific correlation between phases and the change of the density. So this is graphic representation of what's going on. So you start from here. Then in the first layer of mantle, you move along, you precess around this position of the B, and so you end up in this point when it enters the core of the Earth. In the core of the Earth, you have bigger density, and this is the B, which corresponds to the core, and therefore your system starts to oscillate around the core position and will do this motion. And the point 3, it enters again the mantle, and so it will oscillate around this old direction, and it will make this motion. So this type of the oscillatory curve, and this is probability as the function of distance, would correspond to the following motion. Like first the system do this, and that, and then it do this. So that's kind of parametric transition inside the Earth. It may be more complicated, like here. So you see here again, so this is what happens, and you end up in this position, and this is more complicated motion. You start here, then you are getting to this position in the mantle, and then it will make even 2 circles here, you end up here, and in the second mantle layer you are ending up here, having maximal transition of electron neutrino to, say, muon neutrino. So this is what we call oscillogram of the Earth. So this is the Earth in neutrino light, if you want. What is shown here, this is the diagram of energies of neutrinos in GeV, and this is zenith angle. This point corresponds to horizontal direction, so when neutrino is coming this way. This corresponds to vertical direction, when neutrino come vertically from down to up. And you see here the breaking of the picture, and that would correspond to the border between the core and the mantle. So neutrinos which are on the right-hand side cross only the mantle, and here they cross both mantle and the core. So this is just usual MSW resonance, or resonance enhancement of oscillations in the mantle of the Earth due to 1,3 mass splitting. But what is interesting, you have structures here, and they are precisely due to parametric enhancement. So for instance, the point which you saw in the first slide corresponds to this, which means the energy is something like 6 GeVs, and this is cosine of zenith angle. And hopefully these plots will be measured eventually by ORCA and Pingu experiments or things like that. Now, this is not not the only application. So this is IceCube searches for sterile neutrinos. Here delta m squared is different, so you introduce some additional neutrino state, which has bigger mass. Here it's around 1 electron volt, which is relevant for these LSND or mini-Boone anomalies. And so this is the plot from their paper. And you see here again this oscillogram, again cosine, and this is energy. And what you see here is the breaking between core and mantle. And this is the most enhanced region. So this color actually indicates a transition or disappearance. So this is the most strong effect. And it precisely corresponds to this parametric effect. So in the paper first, they have written just usual resonance. But this is due to parametric resonance. When neutrinos cross mantle, then core, then mantle, and you have enhancement. So they haven't seen this effect, and so they put the bound on sterile neutrino parameters. But you see this kind of parametric enhancement helps to get bounds. Now, oscillation in multi-layer medium, that's more relevant for propagation inside the Earth. And inside the Earth, you have, again, this profile, which is with the core. This is the core. And so that is the mantle. And you see here some also layers in the crust of the Earth, or close to the crust of the Earth, or outer mantle. So what is interesting that depending on energy, you can probe different structures with neutrinos. So what you saw before, essentially the effect of this jump between the core and the mantle. And I will show you later that actually these structures can be probed by low energy neutrinos, like for instance solar neutrinos. So let me say a few words about low energy neutrinos propagating inside the Earth. And this is relevant for supernova neutrinos and for solar neutrinos. So as I said already, neutrinos from the sun are arriving as mass states. And the same is for supernova. So neutrinos from supernova will arrive as mass states, as a fluxes of massive neutrinos. So these neutrinos, in fact, are not eigenstates in the matter of the Earth. You need to take matter effect. And so mass states start to oscillate inside the Earth. The mixing angle for mass states is given by this flavor mixing, which we have discussed before, multiplied by flavor mixing in matter. So there is additional parameter, mixing matrix here. So what you are doing is the following. You are going, say, first from eigenstates to flavor states, and then from flavor states to mass states. So that's the sense of this block. What is more important, that essentially only two mixing, or the mixing between the lightest states is important. And this mixing for mass states, nu1 and nu2, is given by this expression. So you can find this from such a formula. What you see here is the following. Let me just focus on this. It's epsilon, which is 2W, V, which is potential energy, over delta m squared. And it's quite small quantity, something like a 3%. If the energy is 10 MeVs, and this is the density in the mantle of the Earth. So it's small parameter, and mixing of mass states is small inside the Earth. Actually, this 3% corresponds to day-night asymmetry, which Super Kamiakande is observing. So Super Kamiakande has found at 3 sigma level the effect of oscillations inside the Earth, and this is 3%. And this is precisely given by this scale, epsilon. And then it is multiplied by sine 2 theta 1, 2 in matter of the Earth, which is close to vacuum mixing. And matter effect is, as I said, inside the Earth is not big. So, but what is important that this mixing angle is proportional to epsilon, and epsilon proportional to the potential, and therefore the mixing angle of mass states in the matter of the Earth is proportional to the potential. Now, how we compute the effects inside the Earth? The structure or the profile of the Earth can be represented as several layers with slowly changing density inside and then jumps on the borders between layers. So this is how profile looks like. And the evolution matrix, or elements of this matrix, moduli square gives the probability. It can be computed in the following way. So you have kind of several elements. You have jump of the density here, and then adiabatic propagation here. Again, jump here, and adiabatic propagation here. And so the evolution matrix is given by the product over all these layers, okay, of these factors. D describes the propagation inside the layer, and it's just simple given by this expression. This is adiabatic approximation with adiabatic phase. And this U, which describe effect of jump of the density on the borders between the layers. So essentially, this matrix is given by usual, say, 2 by 2 matrix of mixing matrix, which is the function of delta theta, change of mixing angle on the border between layers due to change of the density. I don't want to say more about this, but I want to describe results eventually. Results are quite different, quite interesting. So what you can do, you can take, I think probably I have this expression here. Yeah, okay. So if epsilon is small, then this matrix which describes jump of the density is given by just 1 minus the sigma 2, and this is sine delta theta, change of the mixing angle due to change of the density, the jump of the density. Well, let me come back to this. Taking just the lowest approximation which I have described, you can find out that the probability of oscillation of nu1 into nu e is given by this expression. It's a long expression, but it has very interesting interpretation. So there is the first term, which essentially gives you projection of your detected state on the eigenstate inside the last jump. So if your detector is here, your detector is here, that actually gives you effect at this final layer. Now, then you have sum. You may forget about this cosine because this is approximately 1. Then you will have the sum here of the following factors, sum of the following. This is sine delta theta, jump of the mixing angle on the borders, and then cosine, and this is the phase after the jump to the detector. So to say different terms in this sum, and here is just mixing angle in final layer, is the following. So take this layer, and what you see here is some wave which is collected after this layer to the detector. Then another term corresponds to this wave from another layer, and etc. So this expression corresponds to waves emitted from different layers of the Earth. The amplitude of these waves is proportional to the jump of the density or jump of the mixing angle And the phase is just given the phase which is collected after this layer to the detector. So interesting expression, right? And the result will be interference of these waves emitted from different density layers. So here is expression for the sine delta theta, and it is proportional, of course, to jump of the density or jump change of the potential with then some trivial factors, depends on energy. And so your final result is actually described by interference of these waves emitted from different layers. And here you see dependence of day-night asymmetry on the nadir angle. So nadir angle is kind of is not inverse, but is kind of complementary to zenith angle, so that this nadir angle corresponds to horizontal direction, this corresponds to the core, and this is central region. So to describe Earth matter effect, people introduce day-night asymmetry, signal during the night as the function of nadir angle over the day signal minus 1. So you subtract effect during the day, and then this A is describing precisely the effect of oscillations inside the Earth. So this is the detector. Sun is moving, and so neutrinos cross different layers, and you can do scanning of the Earth's density profile. So you have change of the Sun acting as a scanner, right? So if you have enough statistics and the effects are of the order of, say, 3% or smaller, and this is for future detectors. Of course, it's not like now we can do this. That's an interesting possibility because you can scan the Earth's density profile. So this is the result of computations. And here, the integration is done above 11 MeVs for solar neutrinos, and solar neutrinos are up to 14 MeVs. So this integration over high energy tail of the spectrum. And the dependence has very characteristic effect. So here in this outer layer, you have this oscillatory picture, but then there is some dip and then some other things. And features are quite interesting. So one is this dip, which is due to interference of waves emitted from, say, outer layers. And in fact, here, for solar neutrinos, we are sensitive to the structures of the order of 100 kilometers. So since the energy is small, this telescope is sensitive to kind of small structures. For high energies, remember we had this picture for Ice Cube or for this Orca and Pingu, the energies are much higher, 6 GeVs, and they are sensitive to big structures. So the smaller energy, the smaller oscillation lengths, and the smaller structures you can probe with this experiment. So you have this oscillatory picture, which is kind of then averaging. Due to averaging, the amplitude decreases. Then this is interference. Then this is effect of inner layers. And what is interesting, here you see this in these cases, for these trajectories, neutrino cross the core of the Earth. And in the core, the density is 2 times bigger, at least, than in the mantle. So you expect 2 times bigger, at least, oscillation depths. However, there's practically no effect of the core. Now, this is possible, probably, sensitivity to this curve of Dune experiment. Dune, in principle, could measure solar neutrinos, although there are various kind of restrictions and features. We don't know if it's feasible or not. But just for this detector, we made this estimation and have found that that will be sensitivity. Probably with Dune experiment, you may probe this type of the structure. Otherwise, you need to have bigger detectors than Dune to measure these profiles. Now, you see, it was no core effect. And this is because of attenuation effect. So the core doesn't influence much. There is no jump. You would expect naively that here it should go like this by a factor of 2, at least. But there is nothing here. You do not see the core. It's interesting. You do not see the core with this experiment. And what is interesting, Super Kamiokande also cannot see the core of the Earth. So these are Super Kamiokande data. This is during the day, and this is during the night. Okay, the accuracy is very low, so that the only what they can measure is the integral effect, or compare the day signal integrated over the day and night signal. And this is something like 3 sigma. But what is interesting, look at these theoretical predictions. So they made these computations. They made these honest computations. And here, this point corresponds to neutrinos which cross the core of the Earth. And the curves are quite flat. You see, there is no core effect. I even asked the guys from Supercamacanda, so are you sure that you made computations correctly? And they were scared and said, well, okay, we will check, do again the computation. And I said to him, look, no, you know, there is this attenuation effect that they don't know what is attenuation effect. And you see, that's explained why you do not see the core. Also, the density is bigger, potential is bigger, and therefore, the mixing angle of mass states inside the Earth should be bigger. So, you see, this is what you saw already in the previous, some oscillatory pattern, deep, and there is no core here. And the point is that what they are doing, they are measuring neutrino electron scattering. And in neutrino electron scattering, you are not measuring neutrino energy, you kind of measure the energy of electron. And this disappearance of core effect is related to finite resolution, energy resolution of your detector. And here it's, you make this integration. So let me explain this. So we have the formula before, and I will use this. So one can introduce so-called regeneration factor, which is difference of transition probability of the first state to electron neutrino in the case of night trajectory with Earth matter effect and without Earth matter effect. So that's a parameter which we are usually discussing. So here, I had this formula before. You saw this when, so the effect is presented as the sum over waves emitted from different layers. You can get from this formula integral formula, substituting summation by integration, and the formula looks like you see here. So this is again a regeneration effect. This is 1 to mixing in vacuum. And what you see here is the integral from say x0 to x5, final x. Here is potential, and here is sign, and this is the phase from a given point of the trajectory up to detector. Okay? So this is the same as it appears in the summation, the formula with summation. Okay? And the phase is acquired from a given point to final point. So it's given by the integral. This is the difference of eigenvalues. Okay? So this formula actually for potential with jumps of density is reduced precisely to the sum which we have discussed before. Now what is attenuation effect? Attenuation effect is due to finite resolution, energy resolution of your detector or in your oscillation setup. So what you need to do eventually, you need to average or integrate of your regeneration effect over the energy resolution, integrate over energy, right? So this is what we are usually doing. Now, here you have integration over x, here integration over e. If you substitute this, permute these integrations, then you will get this formula, which has very interesting feature. So what you will have here, integration over x, this again vx, this is sine, everything is the same. But instead of this, you will get some function f, function of x and x final. And this function has very interesting features. This is what we call attenuation factor. So here you see dependence of f on the distance, on this difference. So you see what it has. It's 1 when you have 0 distance from a given structure to your detector. And for different distances, depending on energy resolution, you will have this one or that one or this one. You see, the better energy resolution, then the more flat is the function, and therefore you are sensitive to longer structures. So what does it mean, this cut? This means that everything which is, say, in this case, 1,000 kilometers is not seen because this function is just become 0. So this formula tells you that your setup is sensitive to V, to potential or structures in your potential, below something, some distance, which is given by this formula. And this is what we call attenuation length, and this attenuation length is given by oscillation length, and then this energy of neutrino, pi, and this is energy resolution. The smaller sigma E, that is the smaller energy resolution, the better energy resolution, the deeper structures you can see inside the Earth. So this is kind of rather common thing, even microscope or things like that. So the better energy, the better resolution or frequency resolution, the deeper structures you can see. The same is here. Okay? And this is the reason why you do not see the core of the Earth. Neither Super K cannot see nor Dune experiment, because the energy resolution is not strong enough to see structures, say, above 1,000 kilometers. And so you do not see anything. So you can see only the structures which are closer than 1,000 kilometers. So this is approximately the answer. So the answer to this problem of Super K and other experiments is that you do not see the core, you do not see inner structures, because your energy resolution is too bad. Okay? And your kind of distance you can observe is inversely proportional to energy resolution. Well, actually, this attenuation effect has a number of interesting features, which I will not discuss, but just to mention. So this lack of sensitivity to deeper structures actually not complete. Still, you will have effect of the order of epsilon square. You cannot screen everything or attenuate completely. And epsilon square is this 3% square, which is quite small. So you will see effects at the much lower level. So for this channel, which I have discussed, nu1 go to nu e, remote structures are attenuated, and you can see only near structures. Amazingly, if you would have transition of nu e to nu1, in this channel, inversely, you can see remote structures, but you don't see what is in front of you. This is due to T symmetry in this problem. But of course, this is not practically realized. Now, probably I will not bother you too much, but what is attenuation length? Attenuation length has sense, the following sense. Attenuation length is the distance over which oscillations observed with energy resolution sigma E are averaged down. So this is physical meaning of length. So you average these oscillations and you lose the information about remote structures. So actually the averaging in my graphical picture corresponds to the following. You have this polarization vector. And if you have averaging process, remember, without any averaging, without any absorption, you would have just precession around this core. The averaging leads that you will have such a motion, spiral motion, and final after averaging position of your polarization vector will be this. This is essentially the same structure. I don't want to go into details. This is just indication where different jumps are present and sensitive to. Now, beryllium neutrinos can see the core of the Earth for the following reason. Beryllium neutrinos are just line with certain energy, is very narrow line of neutrinos emitted from the sun. And therefore, in this case, as the energy resolution, you need to use the width of beryllium neutrino line, and so sigma E over E is 0.2%. And this is enough to see the core, because attenuation lengths in this case 10 to the 4 kilometers. So, and you see here the effect as a function of Nadir angle for this beryllium neutrinos, and you clearly see that the change of oscillatory pattern when neutrinos start to cross the Earth's core. Well, unfortunately, beryllium neutrinos have low energies, and therefore you just have not enough events even for next generation experiments to see anything. This is the last subject of my lectures, and the most difficult. I don't know if you are still ready. No, maybe first I will stop and please ask me questions about this. Or maybe this. So tell me if you have some questions about.
What is the difference between incoherence and decoherence?
Sorry?
What is the difference between incoherence and decoherence?
Well, here I haven't discussed even coherent and decoherent. I just discussed this averaging, which is in a sense is the effect of decoherence. If you want, you can treat this in this way.
Decoherence means they're losing the coherence to.
Well, one example is you kind of average interference effect. You have no interference effects. If you have two bodies and they are incoherent, then there's no interference between them.
I have a question about parametric resonance.
Yeah.
Can happen also in the solar core?
Well, you have no structures, periodic structures in the core. So I can tell you so that I saw that maybe, you know, the sun vibrates. So there are G modes, and now it looks like they have P modes. And so there is some modulation of profile because of existence of this vibration modes of the sun. But the effect is too small. You may have some kind of parametric effect, but it is too small. And the parameters of these modulations are not fit well to what you have for neutrinos. Well, and now I will talk about something which is, well, I'm working on this now. And partially, I actually were talking about this a year ago when it was the conference in this place. This is very interesting and unusual thing. And I will just tell about things which are more or less established, because there is no end of this story, and we don't know actually what is final effect, collective transformation effects inside the supernova. This is more like for supernova. And this is actually another realization of parametric resonance. You will see this. So in the case of supernova, you are producing neutrinos in very central parts of collapsing star. And so they are propagating toward the surface of the sun, the star, and then in between the star and the Earth, and then may oscillate inside the Earth. And oscillations inside the Earth are essentially the same as we discussed for the sun. You expect some kind of attenuation effects. You expect some effects of this multi-layer medium. So in more or less outer regions, you have MSW transformations. And in this case, two resonances are actually acting. Transformation is adiabatic here, so that everything is very simple, apart from the fact that you may have some effect of shock wave. So shock wave propagates, so it reaches this resonance region, usual MSW resonance region. Actually, I had another slide where it's indicated. And shock wave front can break adiabaticity, and therefore you may expect here adiabaticity violation effects. And you can even trace how a shock wave propagates, in principle, observing neutrinos. Now, in the very central density layers, here the number density of fluxes of neutrinos are so high that you need to actually take into account scattering of neutrinos on neutrinos. And that complicates things enormously. So the scattering of neutrinos to neutrinos proceed via exchange of Z boson. This is for neutrino on neutrino, and this is for neutrino and antineutrino. Here you have annihilation. What we have discussed before is scattering mostly in T channel. So if you have this scattering in T channel, then your electron neutrino go to electron neutrino, and your background neutrino is going to background neutrino. So this elastic forward scattering generates this type of the potential. And now, since both particles are moving, you need to take into account inside the current which contains this vector component. So gamma 2, gamma 3, gamma 1, gamma 2, gamma 3, not only gamma 0. And that produces this product of velocities of electrons and background, velocities of neutrinos, of electron neutrinos, and velocity of background neutrinos. So far, so good, but Pantaleone actually a long time ago observed that it may be the following process: exchange in U channel when electron neutrino with momentum p is transformed to, so electron neutrino with momentum q, which is momentum of initial neutrino b in background, and vice versa. So you have this collision, and electron neutrino pick up momentum of background, and background neutrino pick momentum of electron neutrinos. Okay? So I didn't put here. So this is Q and this is Q, this is P and this is P. So momentum here is the same. But what happens is the flavor changes. So since electron neutrino pick up the momentum of background neutrino, so that's what happens here. You can treat this diagram as momentum exchange or as flavor exchange. So you can see that along this line, which has momentum P, the flavor changes. So electron neutrino is transformed to neutrino B, and neutrino B is transformed to electron neutrino. So this is the key point. I mean, ask me questions. So exchange in U channel can be treated as exchange of momentum for the same flavor, or as exchange of flavor.
Then interference happens between T channel and U channel. Interference.
Sorry?
Interference between T channel and U channel.
Well, no, there is no interference because here you have electron neutrino and here you have neutrino B.
Yeah.
No. So just look at this channel. Do you agree? So you have the following. You have electron neutrino, which changes momentum. So instead of P, you have Q. B has momentum Q, but it has momentum P after collision. So actually, it's bad. So you have collisions of this and that. So what happens? These go to this line, and these go to this line. There is no kind of fundamental change of the flavor. So this is just standard diagram. There is no lepton number violation. So this is important point. But it seems that you have transitions which look like you have change of the flavor. So momentum along this line and this line are conserved. So this is P and this is Q. So it looks like that you have electron neutrino, which is converted to B, and you have B, which is converted to electron neutrino. Agree? No? Ask question, please, because this is, if you disagree with this, then.
So if you think about E-channel, conventional non-relativistic approach assumes the interaction occurs instantaneously.
No, here we have usual weak interactions with very short range interactions, and we have this relativistic neutrino, ultra-relativistic neutrinos. So it's just that you have transition of momentum, right? So you have what you have U, this nu E, and then momentum is transferred to this. So nu E, momentum is transferred to this, and the momentum of here is transferred to E. Nu E. So you have just in some situations you have in some parameter space of this momentum you have this type of the momentum change. Everything is fine, which means that your Z0 will have not 0 Q square, but it has something which leads to this exchange.
So this interaction doesn't occur instantaneously.
No. So that's, I don't know what you mean instantaneously. So these are just the same diagrams. But usually what we are considering that momentum of neutrinos is the same as momentum of neutrino, electron neutrino in final state, and this is the same as this, and q squared is 0 here, q squared. But you have also possibility that momentum of this new E is actually transferred to this new B, and this transforms to this, and therefore q squared is non-zero for this. It's actually minus s or what, I don't remember what it is.
So this neutrino background.
What?
What is the background?
Okay, so just the all neutrinos are kind of background, right, in supernova. I just pick up one of the neutrinos, and then the rest are backgrounds for a given neutrino. Or you mean what is the flavor of this background? It can be tau neutrino or muon neutrino.
I have a naive question. So when you describe this process, you assume there's some background neutrino. So where are they from?
No, I will arrive at a realistic configuration. I'm just saying, suppose you have flux of electron neutrino, and it crosses the flux of neutrinos of type B. And I have this type of the...
The other question, are you trying to include the matter effect?
No, wait. No, it's you are complicating. So, okay, I may write here nu B like nu tau, for instance. Are you happy with this? I just have one neutrino, one-to-one neutrino scattering. No matter, nothing else. So no background. Forget about this background. Just I have scattering of electron neutrinos on tau neutrino or muon neutrino. And then what I see, that if exchange is in T channel, sorry, in U channel, then we have this process. It can be interpreted as transformation of electron neutrino with momentum P into tau neutrino with the same momentum, and tau neutrino with momentum Q to electron neutrino with momentum Q. So no exchange of momentum, however, the flavor exchanges.
New channel occurred twice.
What? Not twice. Take this diagram and see that momentum of this guy, this electron neutrino, is transformed to momentum nu B. So if this is P, then in final state this will have momentum P. If this is Q, momentum Q, then this momentum has Q.
So if they exchange once and exchange again.
Well, if you want, so this exchange with momentum with this and this momentum. So you have this momentum, it exchanged to this, and this will go to this one. And energy momentum conservation is satisfied. There's no problem with this.
Is U channel coherent?
Yeah, it's just 2 by 2 scattering. For time being, there is no coherent issue. It's just elementary process. Elementary process of scattering of, say, electron neutrino on tau neutrino. And it can be some kinematic configuration of this type.
Scattering angle is important.
Well, you need to, so that's, you know, this angle, which angle? So that's, what is important that momentum along this line doesn't change. This angle, of course, can change, this one. So it looks like we have Lepton number violation, right?
Yeah, because mu B is different from mu E, then.
Yeah. Again, if you don't like B, put here tau.
I don't know why you say Lepton number, total initial state and final state we have to compare.
Yeah.
Not only perturbations.
Yeah. So it's again. So what I'm saying is not kind of effective Lepton number violation along a given line, right? So along the given momentum.
It is coherent.
There is no coherence yet, so we will come to this. But We're still trying to make the first step, you know, just to go into the problem. I don't know, I have no blackboard, I don't know. Ah, yes, there is a blackboard. Probably with a kind of, with arrows, I can show you this better. No, there is no piece of chart. Oh, no, there is. There is something. So what is shown here is, let me put, you have electron neutrino colliding with tau neutrino. Now, in final state, you have electron neutrino here, and tau neutrino follows the line of original electron neutrino. So it's Q, and along this line you have, or what is, I have forgotten, what is this? A P. Okay, so this is P, and this is Q.
The mass of two neutrinos are same, they can happen.
Oh, so I don't discuss even the mass. So that's still, forget.
What is your question then?
Wait a minute. So if you agree, so could you switch off? Then I will continue later. So questions will come. Now we're asking, what are your questions to this? If you agree, then we will continue.
Yes, I agree.
Okay. Okay. Now coherence come. Suppose you have this, again, electron neutrino moving in this direction, and it meets background of neutrinos, which can be tau neutrino or something like this. Now, can I have coherent scattering? That is, the amplitude of scattering on different background neutrinos sum up in the amplitude, and they do not kind of destroy each other. Like in the case of, usual matter effect, you have neutrino which propagates in the background of electrons, and everything sums coherently. To have coherence, you shouldn't change background. So background should be in the same state as an initial state. Then you can sum up effects of scattering on different neutrinos. Okay? Now, the point is that, of course, if background neutrinos are purely tau neutrinos, you will not have any coherence because, you know, if you have, say, this is tau neutrino, and I have electron neutrino which go in this way, and therefore this will be the state which is orthogonal to the state when electron neutrino go in this, from this point, or from this point, or from this point, because then I will have background in which I substitute my background neutrinos by electron neutrino, and you will have states, final states, which are orthogonal to each other. The only way I can get coherence is the following. Suppose my background is actually not completely orthogonal to electron neutrino, but my background neutrino contains still some electron neutrino component and tau neutrino. So for instance, if background oscillated somehow before it meets my probe electron neutrino, then I may have coherence. So suppose my background is in this state where these F factors are the amplitudes to find electron neutrino or tau neutrino in the background neutrino of I. Now, inverting this expression, I will get expression of electron neutrino in terms of background and some orthogonal state. So it's just orthogonal combination. With this, I may have the following. I have electron neutrino, as in the previous slide, it go into this direction, and background neutrino will go in this direction. Now, my electron neutrino, according to this formula, has some component which is nu b. So here I show decomposition of my electron neutrino into nu b and nu a, which is another one. Now here, nu b in turns, according to this relation, contains some component of nu tau. And here I show decomposition of my nu b into nu e and nu tau. So now this type of, I have actually 4 different combinations of transitions. In particular, I have transition of electron neutrino to background neutrino, and here background neutrino to tau neutrino. And this transition can be coherent because in this way I do not change background at all. Because here I have again background particle, and so I do not change background. If this scattering occurs on this neutrino, again I will have something which will not change the background state.
I have a question.
Yeah?
Is this possible for us to have the orthogonal state to the electron neutrino state? Because we have the mass mixture for the flavor eigenstates. states. So is this possible? You said that.
Yeah. So it is possible. For instance, suppose I produce somewhere electron neutrino, and then due to oscillations, I can get this type of the mixture. I will show you later. No, for time being, it is just assumption. So my background is actually not just something which is orthogonal electron.
So you mean that the mu A is orthogonal to mu B?
Yes.
I see.
Yeah. Mu A is orthogonal to mu B. So, bottom line, what I will have, using just these lines, this one and that, this line and that, I will have transition of electron neutrino plus background neutrino into tau neutrino and again background neutrino. Of course, I will have also transition when electron neutrino go to nu B and then nu B go to again electron neutrino, but this will be not so interesting, right? So I will have just nu E scattering on background. But among these 4 different combinations, I have this one, which is very interesting, which means that I will have coherent scattering, coherent change of the flavor of electron neutrino to tau neutrino, not changing background. And therefore, scattering on different background particles will be coherent because I do not change background. Yeah, you're looking like I'm cheating, no? No, so this is the key point. I may have coherent scattering, changing flavor, and not changing background. Of course, it will be not 100% because, I need to have decomposition here, and I need to have a decomposition here, and therefore, altogether, this diagram will be proportional to this F-I-E and F-I tau, and this is conjugate, and then I need to sum up over all the particles in the background with which interaction occurs.
Okay.
You still don't agree? No, ask, because I think this is the simplest explanation. You can try. So actually, I get this picture after quite a while, so I'm trying to. Okay? So then what happens is the following. I will get contribution to my Hamiltonian, which has these common factors. So this is because my neutrinos are moving. And then I have this off-diagonal, non-diagonal matrix, which is given these off-diagonal elements. This is what I have just derived for you, appearance of here, which transform for me electron neutrino to tau neutrino. Here is tau neutrino to electron neutrino. And these are diagonal terms when I pick other combinations from my diagram. Okay? So then I can, by the way, so that is written that actually this F, if I have oscillatory origin of this background flavor, then I just given by square root of probability. Suppose I produce electron neutrino, and then, so this function is just proportional to square root of transition of electron neutrino to B. And this function is proportional to transformation of tau to B. Okay? or vice versa, B2 electron, and this B2 tau. So that's actually what we are getting here is the matrix which itself depends on oscillation probabilities. And so this means that the problem becomes nonlinear, right? So we want to compute probabilities, and we have Hamiltonian which depends on probabilities. Now, how do you like this? So eventually this can be rewritten in such a form. I'm introducing potentials, here diagonal, and this is off-diagonal potentials, and this diagonal is just given by probability of E go to B, or B to E, and here is off-diagonal, which is given by square root of probabilities of B go to E and B go to tau. So here is total Hamiltonian. I add to neutrino Hamiltonian also usual matter effect, as we already discussed before, and also vacuum terms. So these are the terms which already you see, and now we have these additional neutrino terms which we have derived. And so this is omega p is just delta m square over 2 energies. And we have these new contributions from neutrino scattering. And they are the functions of probabilities. So we want to use this Hamiltonian to compute probabilities. But Hamiltonian itself depends on probabilities of oscillation transition of different neutrinos. So the problem in this sense becomes nonlinear. Okay? So usually in the central parts of the collapsing star we have this V usual matter potential is much bigger than potential due to neutrino, and this neutrino potential is much bigger than just vacuum term. Now, so I just discussed one momentum of our electron neutrino, one momentum in the background, but actually you need to make integration over all possible momenta of your background neutrinos and directions and production points. So eventually your potentials are given by these multiple integrals over kinematical variables. And now finally we have this expression for total Hamiltonian where potentials are given by these integrals over momenta and production points of neutrinos in the background. So this is the problem we need to solve. We can a little bit simplify this expression, removing phase here. We have the phase here because in general this potential has also the complex phase. And it actually originates from the phases of these potentials. So we can remove this, and then diagonal terms, you see here I excluded here complex phase, are like this, and diagonal terms are given by matter potential. Here is neutrino potential. Here is this vacuum term. And this is interesting term, which is derivative of the phase over the time. And actually, interestingly enough, this actually can cancel this big matter potential, producing eventually big effects. Now, what is the problem? Of course, you need to solve this problem. You need to solve this equation, but for this equation, you need to find these probabilities which enter, in these off-diagonal and diagonal potentials. So for that, you need also solve the equation. So you have infinite, essentially, number, 10 to the 57, or I don't know, 10 to the 50 equations coupled to solve eventually the problem for a given neutrino, which you kind of eventually detect. Now, probably I will not discuss much this. And I will show you solvable example. Maybe that will clarify some points. So let us consider solvable example. We have one electron neutrino, which is propagating in the flux of parallel flux of background neutrinos, which are probably produced also like electron neutrinos. The problem is simplified, of course, because you can compute what is the state of electron neutrinos. Since they are parallel, there is no interaction between neutrinos in this flux. Remember, the potential is proportional to 1 minus velocities. I don't think, yeah, so it's here. So, and if you have parallel flux, then they are not colliding, and therefore you have no potential, neutrino potential for themselves. So they just experience usual oscillations, right? And then your probe neutrino crosses this flux of oscillating neutrinos. In this case, we can explicitly compute potentials. And this is what you see here, that diagonal terms, maybe I start from off-diagonal terms. It's given by some v nu 0, which is just given by total number of neutrinos, multiplied by square root, and this is the probability that electron neutrino to the given point oscillate to tau neutrino. So that's it. And you know what is this, because these are just usual oscillations, and we know what is this p e tau. So it's given by just usual oscillation formula. This is some function of these crossing angles. Anyway, so in this example, we cannot find this. We can find these probabilities, and we can find explicitly the expressions for the potentials. Okay? But still, in this case, we have flavor exchange here, so that's not abolished, right? But it's a solvable example, exactly. So what we have an interesting situation. We have potentials which are periodic functions of time, right? Time when we follow this neutrino. So this neutrino propagates, time is changing, and they meet our background neutrinos at different points with different oscillation values of oscillation probabilities, and therefore this electron neutrino will feel modulating potential. Okay? Good. And so we can expect parametric resonance in this case. And so this is some computations of the form of this potential. They will not be simple sine or cosine, but still they are periodic. So these are the dependencies of the potential on time. So, and this for simplicity consideration for the constant flux. There's constant flux. But this is the shape of the potential for different parameters xi, and this is the ratio of neutrino, total neutrino potential over total potential of electrons, usual potential. So this is for diagonal terms, and this is for, no, this is for off-diagonal terms, so this is for diagonal terms. You see, the shape is not just sine. The sine appears only for very small, when amplitudes are small. Otherwise, it's quite complicated. However, it's periodic, and therefore, it produces some parametric resonance, and you see here the parametric resonance in this omega ratio of probe neutrino to background neutrino energies, or something like this. So you see here parametric resonance, and this is the condition for parametric resonance, which is a relation between diagonal terms and so when you have zero values of diagonal terms. Now that has applications still. Of course, in the case of supernova, you have neutrinos which are flying in different directions, not like you have parallel flux, but it can be immediately applied to such a situation when you have star and then some external neutrino propagates in the region where you have already essentially parallel, or not parallel, but still diverging fluxes of neutrinos which do not interact between each other. So that you can apply immediately this to such a situation. Well, the problem is to solve all these equations for realistic supernova. And one can try some kind of effective theory approach to guess what are these potentials which actually drive this parametric resonance. I will skip some slides by purpose because even marked this that I want to skip. But one can solve inverse problem. That is, people discuss these collective effects, and they have found some interesting situations and some interesting effects like synchronized oscillations, fast flavor transitions, bipolar oscillations, spectral speeds, using some simplified models, oversimplified sometimes, reducing to one-dimensional problem and so on. So they have found these effects. What one can do is to try using this, what I have described before, to find if we can really find the potentials and time dependence of potentials, which can reproduce these effects. Well, it seems it is possible to find some specific time dependence of these potentials. Of course, what I have shown you just for constant density flux. But in the case of supernova, you may have more complicated time dependence. And maybe I will show you just a few slides more. So for instance, you may have strong transitions if you have these diagonal terms in your Hamiltonian to cancel because of the presence of these derivatives. And in some cases, it can be quite systematic. And you may also have this parametric resonance, which I mentioned, because these potentials are generically periodic functions. So they depend on probabilities in very complicated way. But they should have some periodicity. They should have some time dependence of this way. Now, one of the recent developments which people are discussing are so-called fast transitions or instabilities. So usually, approach to this problem is the following. You describe these transitions not like following individual neutrinos, by introducing flavor field. And then you are discussing various transformations in the flavor field, which is kind of given by these many neutrinos around. And so you write the equation of motion for this field, and then people observe at some certain under certain simplifications very unusual effects. So you may have some instabilities, for instance, in this flavor field. It's not like you can also introduce flavor field for, say, reactor neutrinos. Nothing is wrong. It's just you will have some flavor field which is kind of periodically changes because of oscillations, right? So, but this is kind of static picture with this kind of oscillation waves. You can introduce also for reactor neutrinos, for everything, for accelerator neutrinos. So they introduce this for this supernova neutrinos. Of course, in the case of reactor neutrinos, there is no instability, so nothing special. It's just trivial picture of usual oscillations. Here they're writing very interesting finding with some approximation, interesting effects. It's just even local instabilities, not like you have spherical symmetry or something like this, but suddenly in some ranges, some distances, some angular distributions, you will have some flavor change, a very fast flavor change, something like that. Now, so we were trying to develop this approach following individual neutrinos, what I have described as an individual neutrino approach. This can be done above neutrino sphere, so-called. So you have neutrinos when they are trapped first in the inner parts, but then they propagate freely. And for this free propagation, you can just follow individual neutrino in very complicated potentials, which we are not knowing. So this is kind of this effective theory approach. So what we are saying, we follow individual neutrino, which will eventually detect in our detectors. And these neutrinos are propagating in very complicated potentials, which have very complicated time dependence. And so this is kind of idea, and then to find what are these time dependencies of these potentials. So one of the effects which I have discussed is parametric effect, which can lead to strong transitions. To have these instabilities, which is exponential change, exponential with time change of the flavor in certain ranges, can be achieved if they have the potential which is not modulated by just periodic as periodic function with constant amplitude, but modulated with growing amplitude, which one can expect because the potentials also depend on the probabilities. In this case, you may get exponential change, exponentially fast change of the flavor. So, and this is kind of graphic of this type of the transitions. So, this is my conclusion. You see, I would probably prefer first to speak on this, because when you are not tired much, and it's a lot of material, right? So this happens what happens. Now, my conclusion is very simple, that theory of neutrino flavor transformations still will play an important role in future developments of neutrino physics. And so we still need to solve and establish mass hierarchy, CP violating phase. We need to search for sterile neutrinos, do oscillation tomography of the Earth. Actually, I'm finishing one of the papers which should appear soon. This, interestingly enough, one can put detectors in South Pole and to use something like an ice cube with low threshold detectors to check what is density distribution and ice distribution in Antarctica. But so this is one of the possible applications. Now, we need to understand supernova neutrinos and also search for new physics. Now, the theory of neutrino flavor transformation is to a large extent elaborated. But still, the theory of collective transformation in realistic supernova is missing. So this is one of the few areas where one really needs to have probably even some conceptual input. So I'm trying with this effective theory. People are running enormous codes to get what happens, or to use some models and simplifications. And in many cases, some effects can be just artifact of these simplifications. So there are still some subtle effects which should be clarified with usual oscillations. Another interesting point that some small effects which were ignored before now may be interesting and important in connection with increase of accuracy of the experiments. And so now we can talk about some effects at the level of, say, percent or sub-percent level, which we ignored before. So the final point is that the new effects of flavor transformations can appear in the presence of new physics. So in the recent days, we are studying these effects of probe of dark universe by neutrinos, filled by something, I don't know, some fuzzy dark matter or some other dark matter. And here we may expect quite interesting effects. For instance, one of the things that if we have scalar field, formed essentially by very light particles with a mass 10 to the minus 20 electron volts, so-called fuzzy dark matter, they form some coherent state which oscillates with time. And so we may have effects around us when you have change of potential produced by this fuzzy dark matter, change with time. And some observable effects are still possible. So this is kind of outline for future. Thank you very much.